You're 2 o'clock.
Oh, hello.
Hello.
Hi, Irina.
So, who is here? Benjamin is already here. Already something.
Alexei, I am confusing with the time. The session will start in 10 minutes, okay? Approximately.
In 7.
7 minutes.
7. Okay, because it's too complicated to understand always. Okay. And my talk will be on Friday, exactly at the same time.
Yeah.
Okay, thank you very much. Thank you for adding my title, so for delay.
We have your title now.
Yes, we have everything. We have everything now.
Okay, very good.
Yeah, now all these 3 days it will be the same. We start this time and finish 6 o'clock Moscow time, including all this discussion. Whatever.
Irina, so on Friday, whole day you will be present. You're muted.
I'm sorry. Maybe during the next break, I will try to share a screen because I see many people had a lot of problem. Yes, because I suppose
not many yet, only 2.
Only 2, okay. Because I suppose maybe I will speak from the sanatorium and I will use my notebook, so I have to check my notebook. Maybe the program I have to renew the Zoom system. Yes, okay. Oh, very interesting conference. Okay.
Yeah,
so Irina, on Friday you will be there whole day.
Yes. I will. Yes. Yeah. I'm still at home. I hope to go to the sanatorium next week, but who knows? Maybe they call us and tell that they have free places just now. Yes. Okay.
And the first speaker is Alessia, yes?
Yes.
By the way, do you know that there is a University of Alexei Starobinsky?
There is what?
Yeah, у него день рождения сегодня у Старобинского. The jubilee, 75.
I actually missed this. I'm sure Facebook reminded me, but I don't see Facebook here. Sravan, you should have told me about this.
Yes, but this is today. This is the reason why I call you a little bit early, just to tell you about
it's today.
this. Yes. You can check. You can, to be absolutely sure, you can check in Wikipedia.
Yes, you can. I cannot, but okay. Let's see.
Okay. If you want, I make a share screen.
No. It's okay. It's okay. No, I will find a way. No, it's a pity thing. Wikipedia is also blocked in China, so it's like usually it's very useful tool, but it is blocked.
But maybe you can check in the academia. No,
of course I can check. It's not a problem. It's not a problem at all.
But anyway, you said, so it's confirmed. No need to check.
Because I checked yesterday, but who knows? Okay.
Well, I don't see anything in Facebook, so usually I get notification.
Okay.
Anyway, it is 19 April. So yeah.
19, yes, today is 19 April, yes. And
yeah, indeed, it's today.
Today, exactly. 75. 75. It's a pity that his talk is not scheduled for today.
But on the other hand, he may have wished to celebrate, so maybe it's correct.
Correct.
And maybe it is very much correct because tomorrow he will share session or chair session of Penrose and other people, and day after he will give a talk. So I think it's all in order.
In order. Okay, very good. Yeah.
No, just a talk during birthday, it may be not easy. He could have other plans.
Yes. Yes. Such kind of talk could be more interesting for us. It could be less formal.
Okay.
After a small drink in the morning. Okay.
Okay, maybe I will message to Alessia. I hope she should appear now.
No, she's not here.
Maybe it was a little bit of too much of courage to put Italians to the first. Alessia, she's Italian, yeah?
Yeah.
To have Italians for the first talk, maybe. But yesterday, Luca came in time to chair, so it's okay.
Then
So
he is
yes,
not Italian, according to your definition.
I guess she's in Canada, or I'm wrong.
I don't know.
No, she's actually now traveling heavily, so I don't know.
Luca, where is Alessia? Do you
know? Good morning. Yeah, she will connect for her session, I guess. She told me.
Yes, actually, it's now.
It is now.
Yeah, right. Maybe I can send her a text.
Yeah, I sent her too, but looks like she didn't see.
I know that after her talk she was busy, but
she is here, right on time.
Whoa.
Hi, Alessia.
Hi.
Hello.
We were just wondering about you.
You are right on time.
Okay. Yes. Okay.
Yes.
So shall I start sharing?
Yes.
Yes, you can try sharing. Yes, for sure. So we have all the speakers. Good.
Wait, this morning is the youngster session. I think is the session with the lowest number of years if we sum our age, which is good. We are the youngest session.
Yeah.
Okay.
Kerry is also young.
I think we can start, right? Good afternoon, good morning, good evening, everybody. We are starting the third day of the conference, and this session has three talks. First by Alessia Platania, then Benjamin Knorr, and then Luca Boninfante. Each speaker has 40 minutes plus 5 minutes of questions. So I would like to ask the people who has questions to wait until the last 5 minutes so that we have the time controlled. And in the last 5 minutes of the 40 minutes, I'm going to raise my hand just for the speaker to know that the time is finishing. So the first talk is by Alessia Platania, who is going to talk about diverging black hole entropy from quantum infrared non-localities. You can start.
Yeah. Thanks Vera for the introduction. And I also would like to thank the organizers for organizing this very nice conference and also for inviting me to contribute. Today, as Vera said, I'm going to talk about this topic. So black hole entropy generated by infrared non-localities. And it is based on a recent paper that I published with my collaborator, Jaime, who is currently a PhD student at the Niels Bohr Institute. Okay, so let me start with an outline and also a spoiler of what the results will be in one slide. So we know there are different approaches to quantum gravity, and each approach has different features and will most probably lead to different physical predictions. And such predictions, at least at an effective level and at least at large distance scales, can be discriminated by comparing and contrasting the effective actions of these approaches. And effective actions are generally local. We know this already from one-loop quantum gravity, where logarithmic terms appear in the action. And going beyond one loop, different approaches would lead to different effective non-localities. And the topic of this talk is infrared non-localities, which appear to be phenomenologically appealing in terms of cosmological models, in particular to explain, for instance, dynamical dark energy. And they also seem to occur in some models of quantum gravity. The question then is, what happens to black hole entropy in this model? And this is what our paper and this talk is about. How does the modified black hole entropy looks like? And the surprising result that I will show you is that the result is that generally the black hole entropy that comes from this type of infrared non-localities diverges, and the modular fine-tuning of the couplings of the coefficients of the theory, and therefore the finiteness of the black hole entropy in the models retaining this type of infrared non-localities is non-trivial, and yields a non-trivial test for both phenomenological models and quantum gravity theories. So let's go step by step, and let's start from a picture of different approaches to quantum gravity. This is what I'm representing here pictorially. This is an imaginary space of all possible theories of quantum gravity. And at the origin of this theory space is the marriage between general relativity and quantum field theory, which we know doesn't work straightforwardly. So it leads to a theory which is either non-renormalizable or non-unitary. And in order to solve this issue, different approaches to quantum gravity moved in these different directions in this space of theories by modifying a little bit of either of these theories or both. And in particular, some approaches moved in the direction of new physics or new principles. So perhaps we need new degrees of freedom or new principles behind our theories. Others tried to modify the theory in terms of its symmetries, so by enhancing or reducing the symmetry of the theory. And others advocated to non-perturbativity. And although these approaches are mathematically apparently different, in principle there could be relations between approaches, and if they would lead to the same physical predictions, then they could be regarded as different mathematical descriptions of the same physics. And in order to draw these connections and to make predictions in general, what we would need is to resum quantum gravitational fluctuations, independent of the specific approach one is looking at. So now, how do we resum? quantum gravitational fluctuations. First, well, the goal would be to make not only predictions, but also contrast different theories and put some constraints into our theories. And the way one should achieve this is by resounding quantum gravitational fluctuations. Of course, there are different methods one can achieve this goal, but at least for approaches to quantum gravity that are more tied to the framework of quantum field theory. So, for instance, asymptotically safe gravity, non-local gravity, some regimes of string theory. It is useful to write this in terms of path integrals and effective actions. In particular, if the fundamental theory has the metric as a fundamental degree of freedom, then the path integral would look like this. So it would be a sum over metric configurations, and the weight will depend on the specific Bayer action of the theory. This is obviously the simplest possible case, the simplest possible scenario. It is possible that in other theories there will be different degrees of freedom. So, for instance, in the loop quantum gravity or spin-form models, the metric would be replaced by the area metric. In string theory, there would be many more fields here, but the concept is still there. And together with the path integral, we can associate an effective action, which is the quantum counterpart of the classical of Bayer action. So now this connection, as I said, is more straightforward for approaches to quantum gravity that are based or related to quantum field theory. But this can be generalized with different degrees of freedom, different symmetries characterizing the Bayer action, and even in approaches that are not directly related to quantum field theory, it is expected that at least at large distance scales, one should recover this framework, and one could write down quantum corrections in terms of an effective action. The connection is more difficult in case of discrete theories, but even then, a connection at least at the large distance scales should be drawn. And in the moment one comes up or drives an effective action, then it is possible to extract predictions which are related to the variations of the effective actions. And the simplest case is just taking the first derivative, as this gives the fully quantum equation of motion, and one can then understand how solutions are modified, so how the solutions in general relativity are replaced by their quantum counterpart, and also whether there are additional solutions. Moreover, higher order variations and contractions between them give access to dressed scattering amplitudes, since the effective actions contains already all quantum effects at all loops. So now, how do we characterize effective actions, and why are they so useful in contrasting approaches to quantum gravity? One can write down the effective action. At least at large distance scales, one should try to recover the metric description, even in the approaches to quantum gravity where this is not the main, the fundamental degree of freedom of the theory. And for diffeomorphism invariant theories, one would have generally the Einstein-Hilbert term plus a number of higher derivative contributions. And in general, higher derivative contributions may be written as an expansion, a curvature expansion of this form, where form factors appear. So here for the purpose of the talk, actually, I'm showing all of these free contributions. One of them could be eliminated by the Gauss-Bonnet identity and higher order versions of it. But for computational, but in the context of computation of black hole entropy, such identity cannot really be used. So I'm showing here the full basis of higher derivative corrections. And so in different approaches to quantum gravity, one would have different form factors of the D'Alembert operator. So different quantum gravity theories would give rise to different form factors in the effective action. And there are two ways one can look at this type of contribution. In a top-down approach, what one should do is to start from a given approach to quantum gravity, sit down, do computations, and then determine these form factors from first principle computations, which could involve path integrals, renormalization group techniques, scattering amplitudes, and so on and so forth. But one could also look at these actions, parameterize the version of the effective action with expansions of the form factors, and put constraints of them, do model building. So try to see which type of form factors would be phenomenologically viable or phenomenologically appealing. And on the other hand, use consistency constraints to determine which coefficients should stay in the expansions of the effective actions, or what are their bounds. And this can come, for instance, from positivity bounds, so requirements of unitarity, causality, but also stability, considerations related to black hole physics, and effective field theory arguments. Plus the bonus, one could put some constraints, probably not very strong constraints, using observations. Now, let's try to see how these form factors would look like in different approaches to quantum gravity. So there have been a number of works in this direction, some more based on model buildings, other more fundamental, but it seems that these form factors, so here I'm just using a general FI, they might be different from each other. They typically are non-local. They can have either ultraviolet or infrared non-localities. And this is the case for non-local gravity, which is characterized by exponential form factors, spin-fold models where the form factor are of this form, asymptotic safety models where the requirement of reaching an interacting fixed point requires this type of form factors or similar, and other models where operators of the Polyakov type emerge, so inverse powers of the box operator. So if one would like to parameterize this type of form factors coming from different approaches to quantum gravity, or even models trying to mimic approaches to quantum gravity, then one would have expansions of this form. So the form factors would be written as a sum of both positive degree operators and negative degree operator. At least this formula would hold within the annulus of convergence of these form factors. And well, here I'm writing like infinite sum, but more typically the negative degree operators would be relevant. Only a few, the first few orders would be relevant in quantum gravity or a phenomenological application. And phenomenological applications are indeed a motivation for this type of negative degree non-localities, so operators of the Polyakov type. And they appeared in several phenomenological models that were put out by the group of Luca Mendola, Rami, and so on, Pozziello, the models of Desiree Woodard, Maggiore, Vettrick with the models of quintessence. And they seem to be particularly appealing because you can understand that something like 1 over box at higher orders in a curvature expansion of the effective action would give contributions that are kind of comparable to those of general relativity. And therefore, they are phenomenologically appealing because, first of all, they would lead to deviations to general relativity at large distance scales. One can put constraints. And at the same time, they can, so the appealing and models for dynamical dark energy. And for, as far as to my best knowledge, they seem to be compatible with observations, at least if one doesn't have strong infrared non-localities. So something like 1 over box or 1 over box square seems to be viable observationally. And this would be a motivation from cosmology. Another motivation comes from black hole physics, because alternatives to Schwarzschild black holes cannot necessarily come from a principle of least action. And in particular, there are bounds on what type of model could come from a gravitational effective action, at least if one requires the large distance action to be local. But if one allows for infrared non-localities, for instance, operators of this form, then it seems that there are a number of popular models of regular black holes or wormholes, which can be viable also from a fundamental point of view. So now we know that I just said, and I hope I convinced you that this type of infrared non-localities of the Polyakov type, or even higher order of the inverse D'Alembert operator, lead to large-scale deviations from general relativity, which seems to be controlled and compatible with observations if these operators are too non-local. So if the degree of the operator is not too large. But then the question is, what happens to black hole entropy? Since we know by Wald formula that this type of or any type of higher derivative correction to the action impacts the Wald, will enter the Wald formula, and therefore will lead to corrections to the black hole entropy. A classic and an important example is that of one-loop corrections. So if I start from one-loop quantum gravity, where the form factors are logarithm, then there will be logarithmic corrections to the area law. And in general, beyond the logarithm, the form factors will also have this type of contributions. So with an expansion in D'Alembert operators with both positive and negative degree terms. And the positive degree terms have been analyzed already in the literature. They are in particular of interest for the non-local gravity community. And indeed, within the non-local gravity community, it has been shown that this type of corrections, so only for n positive, leads to subleading corrections to the Bekenstein-Hawking area law. And in particular, these corrections are of this type. So they depend on the inverse horizon radius. And so just by using naive similar arguments, one would expect that negative degree terms would lead to similar corrections, but with a plus sign. So with contributions that are dominant over the Bekenstein-Hawking contribution. And one of the main starting motivation of our work was indeed to test this expectation. And the next question is how dominant they are. And in the computation, there are a number of caveats that one should take into account, because technically, if one has infrared non-localities, one cannot directly apply Wald formula, so one has to go through a localization procedure of the effective action. And there are a number of, one has to be careful with this type of computations due to these non-localities. So now I'm going to give you some of the details about these computations. So in order to make computations doable, we focused on the case of large black holes, such that a number of simplification comes in. We only study the case of static black holes, otherwise one would need a generalization of a Wald entropy formula. And we also focus on the case of spherically symmetric and asymptotically flat black holes. So that the metric would look like this. In general, one would have different metric coefficients. And since we are focusing on the case of large black holes, then one can assume small deviations from Schwarzschild black holes, which we parameterize with this type of 1/r to some power contribution. And as I said, the positive degree term have been, the corrections from the positive degree terms have been computed already in the literature. And what we focused on was the principal part of the Laurent expansion of the form factors. So we only have a sum over some terms of this form. So there will be box to minus n operators that are weighted by some coefficients Cin. So the I refers to the form factor and the n to the degree of this operator, the power of this operator. As I mentioned, the intermediate step is a localization procedure of the effective action, because the Wald formula cannot be directly applied if operators are not locally defined. And therefore, it is important to essentially redefine the effective action in terms of additional constrained fields via a set of Lagrange multiplier. This is just a technical aspect, so I will not spend a lot of time on it. And after some algebra, what one gets is that the dimensionless, the corrections to the dimensionless version of the entropy look like this. So essentially, the dimensionless correction means that I simply eliminated the standard area over 4G contribution. So I'm just focusing on the corrections to the one in the entropy formula. And here there is a limit as R goes to the event horizon, the position of the event horizon. And there are contributions from this 1/, box to n operators at each order n, which are weighted by the Ci operator. Remember that there are free form factors at quadratic order. And these are I'm not writing them down because they are kind of lengthy and it's not so useful to look at them. but they are essentially functions of this FTT and FRR. And I'm now noticing that I used here a different notation. So these G and F are exactly these two lapse functions. So the TT component of the metric and the RR component of the metric. And at this point, so the what one needs to compute is the action of the 1/box operators on functions, general functions of these of the lapse functions of the metric components. In particular, this can be done recursively. So one can start with the order 1, and then the next order operators can be computed starting from the first one. And this also means that the result of one particular contribution to the entropy formula is tied to the previous one. In particular, for the case of n equal to 1, one would have that the action of 1/box over a generic function phi of r would be given by this formula that depends on the metric coefficients and the function phi itself, and some initial conditions that I'm calling Rx and Ry. So they are initial conditions because essentially this formula comes from by solving the action of the box to something operator on a function, and by inverting it. And so the resolution of this differential equation clearly depends on the initial conditions. But we will see that the result in the end does not depend on these functions here, or on these constants. Okay, so let's now look at this entropy correction. And I'm setting here n equal to 1. So we're looking now at the corrections, the first correction to the entropy formula coming from 1/box operators. And this is what I'm plotting in these two plots. So this is minus the correction against R over RS. RS is the Schwarzschild radius. And these plots in particular show the behavior of the entropy as a function of R for specific values of the parameters. As I have mentioned before, so the entropy contribution have to be computed as R goes to the event horizon. And in order to show the result, which would be infinity, I'm just showing this as a function of R. So as a reminder, the lapse function looks like this. And here, for presentational purposes, we set the two lapse functions to be the same, but the result is independent of whether one does this. And if an event horizon exists for a given solution, then it is located approximately at this point. So it is a small modification from the Schwarzschild radius for large black holes. And it depends on alpha, which is this exponent here from the first correction. And it depends on A, which is a dimensionless version of this coefficient here. And what one can see from this plot is that as one takes the limit R that goes to the location of the event horizon, which is shown as these dotted or dashed lines in these two plots, then the entropy diverges. Of course, this is the case only when an event horizon exists. So here, if one essentially takes this A too large, then the deviation from the Schwarzschild metric would be larger, and this can in principle destroy the event horizon. And if one destroys the event horizon, then the entropy is perfectly finite because there is no horizon at any space-time point. But if an horizon exists, as is shown by these lines, these dotted lines, then the entropy diverges exactly once one takes the limit as R goes to the location of the event horizon. And in particular, since the first contribution diverges, also higher order contributions coming from higher order powers of the 1/box operator will lead to divergences. And in particular, the result is independent of the parameters that one puts in. So these plots correspond to specific values of the CI coefficients that come in front of the 1/box operators in each of the form factors. It is independent of this A, the dimensionless version of this coefficient, and is independent of this alpha. And it is also independent of whether the two lapse functions coincide. So if one has the lapse functions that are different from each other with different A's and different alphas, then one would obtain the same result. And also the result is independent of the initial conditions, which I'm going to show you in the next slide. So this is obviously something to look at, because in the inversion of the in the resolution of the equations involving 1/box operators, there are some initial conditions that are displayed here that arise from solving differential equations to invert the action of a box on a function. So one could wonder whether it is an artifact of special initial conditions. But this seems not to be the case. So in particular, what I'm showing here is the result for a given set of parameters. So the dimensionless version of the parameter A is at 0.1 alpha, that is the exponent of the next to leading order correction to Schwarzschild is set to 6, and then the coefficients of the form factors of the 1/box operators in the form factors are set to 1. And here in the plot we set Rx equal to Ry equal to R to show more easily the result. And what I'm showing here once again is the entropy as a function of R. And as before, the dotted line represents the location of the event horizon, which, as you can see, is smaller than the Schwarzschild radius. And independent of the initial condition, there is a divergence at the event horizon. And this is something that arises from special values of the coefficients in front of the form factor. A question is whether any combination of these coefficients could cancel the divergence, because the divergences are associated with each 1/box operator in the action. So a cancellation for some values of these coefficients in principle might be possible. But this seems to be non-trivial. So one can see that explicitly in the case of charged black holes, where the alpha, so the next to leading order correction, is equal to 2. And then the entropy contribution would actually be the sum of two. One depends on the coefficient C21, and the other is C31, while the third contribution actually vanishes in this case. And this functional phi, which depends on the radial coordinate and the initial conditions, so they essentially are the integral form of the 1/box operator. And both these contributions diverge, and therefore, correspondingly, the entropy can either go to plus infinity or to minus infinity, depending on whether these coefficients are positive, negative, in particular, what is their ratio. And in particular, there is a critical ratio of these two coefficients that come in the effective action, for which the two divergent contribution exactly cancel. But so finding this analytically is very non-trivial, so we had to go numerically. And the relation between the two coefficients to cancel the divergence in terms of the charge over the mass of the black hole in the case of charged black holes is non-trivial. And one should notice that in this case there are only a few parameters. So there will be these two coefficients that are couplings in the effective actions, and there is only one correction to Schwarzschild, the Schwarzschild scaling. So in a sense, it is easy to cancel the divergence for some already non-trivial function. But in general, one could have also additional 1/box operators. And there will be additional corrections to the Schwarzschild scaling, and therefore, in general, it is extremely non-trivial to cancel this divergence. So this leads me to my summary and conclusions, which is once again the first slide that I have shown you. So there are a number of approaches to quantum gravity, and I believe a particularly efficient way to contrast them and contrast their predictions, but also put constraints that are model independent is by looking at effective actions and parameterize them in terms of form factors, where each of the form factors can have different effective non-localities depending on the specific approach to quantum gravity one is looking at. There can be, in principle, positive degree terms as well as inverse powers of the D'Alembertian operator. And this type of infrared non-localities have been used in phenomenological models as dark energy mimicker, and also in the context of black hole physics, they seem to be appealing because they can reproduce some solutions for regular and wormhole models. And this also seems to occur in some approaches to quantum gravity, at least in some regimes. And a key question is what happens to black hole entropy, since one would expect that they would also lead to dominant contributions over the Bekenstein-Hawking scaling. And what we found is that the contribution is not only dominant, but it is generally divergent for large black holes, unless one fine-tunes the infinitely many parameters in the effective action such that this divergence is exactly cancelled. So quantum gravity models and the phenomenological models, which deal with this type of infrared non-localities, should predict exactly the coefficients such that the entropy is finite. And so this is not only an intriguing result, but it is also a non-trivial test for phenomenological model and quantum gravity theories as well. And with this, I thank you for your attention.
Okay, thank you very much for your presentation. There is a question from Huang Wu.
Yeah, I have a question. How do renormalization of the diversion of the entropy and this modify black hole entropy. So the how this model so this model have the solution of the information paradox.
So the problem is also that the information paradox is a non-perturbative problem that one should really look at the evaporation till the end. So until the black hole is completely evaporated. And what we are looking at is the entropy of large black holes. So we cannot really say much about information loss paradox.
Yeah. And the color term of this of the diversion.
Sorry?
The cancellation of the diversion.
Mm-hmm.
In the different case black hole.
Yes. So essentially, the cancellation is only possible for the specific values of the coefficients in the effective action, and these coefficients have to come from the specific quantum gravity dynamics. So if a theory of quantum gravity predicts infrared localities, in order to be consistent, it also has to predict the specific coefficients such that the divergences cancel out.
Okay.
Okay, there is another question on the chat by Robert Brandenberg, but since we are already short of time, I suggest to postpone this question to the discussion session afterwards. So thank you again, Alessia Platania, for your presentation. And the next speaker is Benjamin Knorr.
Yes, let me share my screen. Can you hear me?
Yes. Yes.
Yeah, great.
Okay.
Let's see.
So
can you see my?
Yes, I can see your screen.
Okay.
And the title of his talk is Renormalization of Essential Operators in Asymptotic Safety, a Status Report. You have 40 minutes, and at the 35 minute, I'm going to raise my hand to say that you are entering your last 5 minutes.
Yeah, sounds good. Yeah, thank you very much also to the organizers for inviting me. So in preparing this talk, I realized it's less of a status report because unfortunately the results that I would like have presented are not there yet quite. So I will spend a little bit more time on introducing and giving you the big picture here. And I would like to start really with a perspective on quantum gravity, and this will resonate a little bit with Astrid's talk yesterday. So what is really the issue or the big questions that we have in quantum gravity? So observationally, we have these big questions like what happened at the Big Bang? What's the start of our universe, if you want? Or what happens inside of black holes? So these are really very hard to access experimentally. And we have to come up with some good ideas what happens in the universe in these regimes, in these very extreme regimes of physics. And now, of course, unfortunately, as I just said, there's a lack of smoking gun quantum gravity experiments. We cannot look inside of a black hole. We cannot really go back in time and see what happened at the Big Bang. And while this lack of experiments or observations is, of course, a problem for us theorists, because experiments can guide theory development. Now, this situation has brought us into a point where we have a lot of big ideas and even bigger claims in quantum gravity. But then I think it's also sometimes good to take a step back and ask yourself, why should I even trust any particular approach or any idea if I can't test it? Because by now there's such a proliferation of ideas and theories that it's really hard to make a strong argument for one or the other. So this is my general, where I'm coming from here. And to kind of fight this problem, I want to give you a recipe to come up with a falsifiable and predictive quantum gravity theory. And this is like my general spirit that I am trying to implement in my research. So you should start with some, if you want, axioms, if you're very strict, or just some basic principles to set up your quantum theory of gravity and matter. Of course, if you want to describe the universe, this should at least include the standard model or something that reproduces what we observe. Once you've set that up, you have to, of course, check that it's theoretically consistent. It's, for example, unitary, it should be causal, at least macroscopically. But also it should reproduce the experimental data, or at least be consistent with the experimental data that we have access to. Something like cosmological evolution, particle masses of let's say, an electron, a top quark, you name it. So that's a really big set of data that you have to reproduce, both theory and experimental data, right? So once you have that, you can say, okay, that there is a chance for my theory to actually describe our universe. And I think only then you should really ask the big questions, like what happens with black holes, what happens at the Big Bang? Because as I said, by now we have so many ideas and theories, we have to kill some of them. We have to falsify some of them to really make progress. Of course, this is a bit less glamorous and more down to earth. You cannot make these big claims saying, oh, you've solved, I don't know, the information paradox, or you know how black holes look like, you know what happened at the Big Bang. But I think it's a bit more honest and a bit more trustworthy. So you fix your starting point and then you see how far you get. And this is my general philosophy here in this talk, and also more generally. Now, more specifically, my working hypothesis is that quantum field theory works also for quantum gravity. And so the basic idea behind that is, of course, asymptotic safety. And we've heard a little bit about this also in Astrid's talk yesterday. The big advantage in this assumption is that we have access to standard QFT notions like the renormalization group, or in particular scattering amplitudes. And really these scattering amplitudes are what are driving my research at the moment, because they are, of course, related directly to observables, like a scattering cross-section. And in this talk, I want to give you a perspective to how I'm working towards scattering amplitudes in asymptotic safety, in particular, like the simplest that you can imagine, like 2-to-2 scattering. But I think that the general ideas can be carried over to other approaches, because in the end, as I said, you want to look at observables, and this should be a goal for any quantum gravity approach. I think there's something in the chat, but I unfortunately cannot open it. Is it a question?
It's a message from Alessia. Well, I think you can keep going.
Okay, then I continue. So yeah, this is the general perspective. So let me give you the outline of my talk. At first, I will introduce a little bit some notions and some ideas about scattering amplitudes, about field redefinitions and essential and inessential couplings. Then I will zoom in to essential couplings in quantum gravity in particular. And then I will give you some selected results that we obtained from applying renormalization group ideas on these essential couplings in quantum gravity. Good. Now, scattering amplitudes. This is really a topic that has only started recently, that we looked into it within asymptotic safety. Because if you look at the literature of the last 25 or 30 years, most investigations have been at the level of off-shell RG flows. And there come some complications with these off-shell RG flows, of course, because there are residual dependencies on artificial choices like parameterization, gauge choice, and so on. And of course, looking at actual observables like scattering amplitudes, you get rid of these dependencies and you can make stronger statements, because the scattering amplitudes are on shell and related to observables. Now, okay, of course, there's some asterisk here. Some conditions apply. There is some fine print to this, and I will come to that in the next couple of slides. In all of this, now, once you're at the level of observables, for example, a scattering amplitude, or also actually at the path integral level, you can do field redefinitions. Not any field redefinition, of course, should be bijective and so on, but you can do field redefinitions. And the consequence of that is the notion of essential and inessential coupling. And it turns out that what we call essential coupling is what appears in observables, and inessential couplings can be rescaled or even set to 0 sometimes by a field redefinition, and in the end imposing an RG condition. So another way to characterize an inessential coupling is that if you look at an action, an inessential coupling multiplies the equation of motion in the action. For example, just the equation of motion itself or powers of it could multiply also other operators and the equation of motion, but at least there's one power of the equation of motion multiplying it. Now, of course, once again, there is an asterisk here. It's not always true that you can fix it arbitrarily, these essential couplings, and also here some conditions apply, and I will come to that in a moment. In my talk, I will mostly use and talk about the effective action. We've heard a little bit about the effective action also in Alessia's talk just before me. And for now, I will talk about an exact theory. So I will assume that I have a complete effective action, you give it to me, and then I will talk about a little bit what can we learn from this. And later I will also speak a little bit about what it means to go into approximations of the effective action. There's one more assumption here, namely that I don't want to be in the too strongly interacting regime, in quotation marks. Of course, I cannot really define this mathematically precisely, but what I have in mind is some hierarchy in the importance of correlation functions. And you can achieve this if you really do an on-shell expansion. And this, I believe this is central to make sense of this, but I cannot make really strong statements yet. I still am working on making this a little bit more precise. And yeah. Just as a reminder, what is the effective action? You've just heard it by Alessia. The effective action includes all the quantum effects. And the nice thing for me here, looking at scattering amplitudes, is that you can obtain these scattering amplitudes from tree-level diagrams. So no need to compute higher loop amplitudes and do them. That's all already included in the effective action in the tree-level correlation functions. So just to make this, to drive this point home, look at a 2-to-2 scattering. You have these two types of diagrams. You have, so here I depicted an S-channel diagram, but you could have, depending on process, T and U channels as well on the left. And then the renormalized vertex itself on the right. These are the two diagrams that we are interested in. Good. Now let me get into field redefinitions a little bit, just to warm up and to give you a better understanding about these essential and inessential couplings, if you've not heard about them in detail before. For this, consider a standard scalar field theory in Minkowski space. By standard, I really mean like no weird stuff, no extra modes, no ghost modes in particular. And in such a theory, you can, of course, rescale the field with a momentum-dependent wave function renormalization. And this means that you can bring your propagator into a p-squared form and move all the non-trivial momentum dependence into the vertices, which means that all the couplings corresponding to p to the 4, p to the 6, p to the 8, and so on are inessential because you can't put them to 0. Note that you cannot put the p-squared term to 0 because then you remove the kinetics of your theory, right? So this is one of the conditions that apply. You should not remove the dynamics of your theory. There's, of course, another caveat here. For this field redefinition to make sense, you need that this wave function renormalization is positive, and that's that you cannot really remove or add modes. But even there it's kind of not obvious in an interacting theory, because if you would remove or add a pole, of course it would pop up in interactions again. So it's not entirely obvious that you couldn't do that, but I'm not sure that this has been investigated in a lot of detail. Another question mark that I have here is branch cuts. Of course, we know that at the one loop level, we get logarithms. In particular, if you have massless particles, we have logarithms of p squared. And then we have to ask the question eventually, what happens to these branch cuts under field redefinitions? And at the moment, I do not have an answer for that. A second example that I want to give here, since it's like these higher derivative theories came up in several talks already in this conference. Now, this is a really ugly theory, you would think. It's definitely higher derivatives and even non-local. But let me rewrite this theory. And you see that this is literally the same theory, just rewritten. And you see this is just a way to write a scalar field theory, which has two non-ghostly modes. So if you take the second derivative of this and invert it, you get a propagator, and you see you just have two modes that are propagating here, both with a positive residue. This is just basically a point that you can have weird stuff if you allow for general momentum dependence, and you can have situations where you have more modes that are non-ghostly in particular. Now, let me go to gravity a little bit. Now consider a Starobinsky type theory, so an R plus R squared. Here, the spectrum is that of general relativity, or H and Hilbert, plus a massive scalar. And now if you do a field redefinition of this theory, you can change the value of the R squared coupling, which is related to the mass of the massive scalar in the end, but you cannot set it to 0 once again, because you would remove a mode and then you're changing the theory. So all these examples hopefully give you an idea of what you have to keep in mind when you do these field redefinitions, and that it's really a bit non-trivial, and that you should actually spend some time thinking about what you are doing, and that you have to make clear the assumptions that you are making. So as a kind of summary, what are the lessons learned here? So in practice, what you have to do in any theory that you're investigating, you have to choose the universality class beforehand. What I mean by that is you have to tell me what are the modes that you are expecting in your theory. Is it, for example, if you are talking about gravity, do you have just the massless graviton, or do you have the Starobinsky type R² scalar mode on top of that? And depending on what you have or want to investigate, of course, these are completely different theories. And you have to do that because you have to make some choices when you're computing, for example, the RG flow. You have to adapt the regularization, and you have to make specific choices for the inessential couplings. This is not only to simplify computations, but also to make sure that you're actually studying the theory that you want to study. To come back to this example of Starobinsky, in the Starobinsky universality class, if you want to call it like that, you cannot set the R² coupling to 0. But if you're in the universality class of general relativity, you can, because you do not want these extra modes. Also, there's once again this hierarchy that plays a role here, and this idea of expanding about an on-shell configuration, which is really important. You kind of have to choose what you mean by on-shell. What is the specific solution of the equations of motion that specifies the dynamics that you are investigating? And as I mentioned, there are a lot of question marks, at least for me, in these field redefinitions. How should we treat branch cuts? How should we treat some of these infrared non-localities that we just heard about? How should we treat bound states? It's completely non-obvious to me. So there are a lot of question marks, but I think I'm also a practical person, so I like to do computations first and then ask later whether we can solve these problems or whether there have been problems in the first place, because that's also how you make progress. A second point that I want to make here is really about the interpretation of approximations from this perspective of field redefinitions. And I think this is kind of important and clarifies what we do in asymptotic safety, and clarifies also addresses some criticism. So how you should think about computations of the RG flow is that you choose the universality class first. You then adapt a field redefinition to remove the inessential operators, and then you approximate. In this way, you keep the spectrum of your theory from start to end, and then everything makes sense. And conceptually, but not mathematically, that's different from making first an approximation, which might introduce extra modes, and then doing a field redefinition, by which you might remove extra modes again. And in particular, if you do not do field redefinitions, if you do a standard RG flow, and something like a derivative expansion, you invariably introduce extra modes. There's no way around that. This was shown in these two nice papers by Alessia and Christoph Wetterich. So even in perfectly healthy and positive theories, if you do certain approximations like a derivative expansion, you get ghost modes that are spurious. And if you come from this perspective, well, I first choose the universality class and then remove everything that I don't want, which would also change my spectrum, you should be fine. In the following, I will discuss the universality class of GR. And when I talk about matter, it's the standard matter, so a p² type matter. And this means that I only want the standard modes that we observe in GR or in the standard model. I don't want extra modes. I don't, especially not ghostly, but also not of normal type. The philosophy that I also follow here is that a kind of minimal essential idea is that any inessential couplings that can be set to 0 should be set to 0, because this is really the simplest thing that you can have. Because of course you can set inessential couplings to any value, basically, as long as, once again, you don't change the spectrum, but this makes it more complicated in practice. And at the level of scattering amplitudes, what this means is that you put all the complications into this right diagram. So all the complication comes in the 4-field correlation function. Okay, with this general setup, let me now come more specifically to quantum gravity. And I should say, really, I will talk about essential couplings in the universality class of GR. So what can we do in gravity? How does a general field redefinition look like? So we can take the metric, we can rescale it by a constant, we can add a function of the box operator acting on the Ricci tensor, can add another function of box acting on the Ricci scalar times the metric, and so on. So this is kind of a curvature expansion of a field redefinition, if you want. Now, of course, there is immediately the question, well, is this still a Lorentzian metric? I don't know, depends. It's intentionally a little bit small because I do not want to address this question, because it's a really hard question that you really can only answer in the end once you've computed everything. What does it mean for the effective action? Once again, I'm looking at a curvature expansion here in the minimal scheme. And really, this is it, 2 cubic order. You have cosmological constant, you have the Ricci scalar term. The third term is the Euler density, so topological term in 4 dimensions. It's not topological in higher dimensions, times a coupling theta. And then there's the y cubed term. So C is the Y tensor. It's a bit schematic here. And times a coupling. And then you have higher order terms. Note that here only one of the 2 couplings, G and so the Newton's coupling and the cosmological constant, is essential. But we cannot set either to 0 generically, because if you would set the cosmological constant to 0, this is of course related to dynamics, and this comes out of the equations of motion. But you can also not set the Newton's coupling to 0, because then you do not have gravity anymore. But really only one of the combinations is essential. So for example, the product of G and lambda, which is dimensionless in 4 dimensions, is essential. Good. How do we arrive at this? So of course, there's some reasoning why the terms that I'm not listing here in this ansatz are inessential, because they really multiply the equations of motion. And I want to drive this point home with some more details here. So the terms that are quadratic in curvature that are not listed here are inessential because they multiply the equations of motion. And I try to illustrate that here. First line is just a form factor of R squared type, if you want, just that I added terms that are proportional to the equation of motion. So to complete the praised equation of motion, if you want. So we know that R minus 2d over d minus 2 lambda plus higher order terms, which come from Y tensors and higher order essential couplings, is the traced equation of motion. So clearly, since this form factor multiplies the equation of motion, it must be inessential. Once again, assuming that no new modes are introduced. The same thing happens in the second line, as here is the traceless Ricci tensor, which vanishes for GR, but has some value if you include the C cube term. And once again, you get a form factor related to that. But since we write this down in terms of the equations of motion, this must be inessential. Now you could wonder about a form factor acting on the Y tensor, but this neat identity, which comes from the Bianchi identity, that a box acting on a Y tensor can be written without approximation in terms of derivatives acting on the trace Ricci and the Ricci scalar. Good, this removes the quadratic terms, except of course for the topological term, which is essential. For the cubic terms, basically the same thing happens. almost all the cubic terms that you can write down are inessential. And the only exception for that is the Gauss-Zanotti term. And in higher dimensions, you have a second combination of C cube, which is independent, but which is not independent in 4 dimensions. So I didn't write it down. In particular, there's no essential coupling, which has either 2 or 4 or up to 12 covariant derivatives acting on Weyl tensors, where the indices are contracted with the Weyl tensors. And you can show that explicitly by using Bianchi identities and partial integration. This is some work to show. It's not completely obvious if you just look at it. It's just a computation that you have to do. That, of course, the terms that include Ricci scalars or Ricci tensors or traceless Ricci tensors, they are related to the equation of motion. So all of them are inessential. Now, also a form factor contribution to this Gauss-Zanotti term is inessential, once again, because of this nice identity that box Weyl is dependent. Good. For higher order terms, that's where the fun starts, really. By extending this argument, using the equations of motion to determine what is essential and inessential, you see that the essential operators can only contain the Weyl tensor and covariant derivatives, and in particular, no Laplacians or box acting on a single Weyl tensor. And you should structurally think of, for example, the 4-point function, so 4 Weyl tensors, as something, a function. Of course, this is now in momentum space, so S and T are Mandelstam variables, but some operator generalization of that. This is the most general thing that you can have at curvature 4 tensor, which is essential. And not writing this out in covariant rate. Which really means that coming back to this amplitude, or these diagrams contributing to a scattering amplitude, this is really what enters this on-shell amplitude rate, right? So the right diagram, if you have the external legs on shell, this depends on 2 Mandelstam variables, which are independent. So this really makes sense that you can parameterize the essential couplings in the 4-point function by a function with 2 momentum arguments. So this really drives the idea home that essential couplings are really related to on-shell amplitudes. And this whole argument also tells you that this left diagram is really, in a sense, coming from a purely local theory, if you think of an expansion around flat background, because the propagator is the GR propagator, the 3-point vertex is GR plus Weyl cube, and that's it. All the non-trivial bit is in the 4-point function, as I've said before. But here you can see it explicitly and really make it explicit also at the level of the action. So as I just said, so if you're in this universality class, the non-trivial scattering physics starts at 4-point function. Big oof, that's really hard to compute, of course, but this is how it is. By these field redefinitions, you can just push all the non-trivial physics into this one diagram. It's still the simplest possibility in a sense, because you can of course look into other schemes where you have some of the non-trivial bit in the S-channel diagram, but it doesn't help you. I mean, a 2-to-2 scattering amplitude always has this this renormalized vertex, so you cannot win anything here. So there's no free lunch. Another thing where you do not have free lunch is that if you're in practice computing the RG flow, you have to impose these field redefinitions consistently along the RG flow. And while this reduces the complexity in practice, there's still no free lunch, and you have to compute running field redefinitions. That's more of a practical point here. And finally, once we think about matter and not only gravity, this whole essential and inessential business gives you also the result that non-minimal couplings to matter are really hard to probe in the end, because usually the lowest order operators either involve the Ricci scalar or the Ricci tensor. These are in essentials, so you have to build something with the Y tensor. And in fact, the lowest order or lowest mass dimension operator that you can write down, which is a non-minimal coupling between matter and gravity, is exactly this operator, Y tensor coupling to two field strength tensors of, say, a photon. And for example, if you have a scalar field, the only thing that you can build is something like a c squared phi squared. And this is already pretty high mass dimension. So generally, if you accept the idea that you can do field redefinitions, probing non-minimal couplings is really tough. Good. Now this is the general idea and the general perspective that I have on essential couplings, field redefinitions, and where I want to go. And out in the remaining like 7 minutes or so, I want to pick some results of the last years and also ongoing work in computing some of the RG flow of these essential couplings. And this is really a recent development because only in like 2 years ago, since 2 years ago, we have actually access and an FRG equation has been formulated to take into account essential versus inessential couplings in these two papers. Good. I want to start with a work in progress together with Baldazzi, Force, and Clute. And here we are actually considering a derivative expansion up to 6 orders, so 6 derivatives in 4 dimensions. And here for interpretation, again, it's important that we first choose the universality class, so GR, and then do the field redefinition at this level so that we do not add or remove modes at any point here. So we're really working with the standard spectrum of GR. And if I've shown you the action to this order, but now without the form factors, looks like this. And now you can sit down and compute the RG flow of all couplings. This is still pretty hard, of course, but we managed to do this. There are 10 running field redefinitions that you have to compute on top of the standard. Yeah.
What is the third term in the action?
I'm sorry?
What is the third term in the action after the Einstein-Hilbert? After the
sorry. This is the Euler density. So E is the Euler density and theta is the coupling of the Euler density.
Okay.
It's a topological term. Yeah, sorry. I mentioned it before, but I didn't mention it again. Yeah. Yeah, so we have the lambda, we have Newton's coupling, we have the theta, which is the topological term, which of course in 4 dimensions does not drive the RG flow since it's topological. And we have the Y cube coupling. And in the end, we only have 2 essential couplings, not counting the topological term because it does not feed into the RG flow, which is the Y cube term, and we chose the Newton's constant. Plus on top these 10 running field redefinitions that I'm not displaying because they are inessential. Good. This is the phase diagram that we get. So what does this mean? The y-axis is the dimensionless Newton's coupling. The x-axis is the dimensionless Y cube coupling. And what you can see are the integral curves of the RG flow. And then there's a central purple dot, which is a UV fixed point realizing asymptotic safety. And then at the bottom, in the middle, you see a red dot, which is just the Gaussian fixed point. And you can see from the lines, the arrows are pointing towards the infrared. This UV fixed point has one relevant direction and one irrelevant direction. I depict the critical exponents on the right. The size doesn't really matter. It's important that one is positive, one is negative. And this tells you that there's really no free parameter here in this theory. Because we have one relevant direction, but we have to fix the scale. So really it boils down to a completely predictive theory, 0 free parameters. And this means that we can actually compute what is the value of the Y cube coupling. And it goes like this. It has a logarithmic running in the infrared, which is the second term, which comes with a universal prefactor, which is regularization independent, and then the numerical like Wilson coefficient, if you want, that just comes out of the computation. So it's really a prediction, if you want, and it comes out to be roughly minus 0.5 in these units of Gn over 16 pi squared. Great. There's more work in progress here that I do not really have time to show you, but what we are working on is really a curvature expansion up to second order. So really to include these momentum dependent field running field redefinitions, as I've showed you in the more general part. This together with Chris Ripken, a former postdoc who unfortunately left science now. Then we are working on an f of r type, but once again in the GR universality class, which means that I want to investigate terms of r to the n, but without this extra mode. This is together with a student of mine. And then I also am investigating questions about general dimension, the gauge dependence, also related to writing down on-chair flow. But this is not the only thing that I'm looking at the moment. I also look at the coupling to matter. And there's one work that I want to point out that came out last year. And here I looked at the derivative expansion, so similar to the first result that I showed you, but only to fourth order, but then including a shift symmetric scalar field phi. So you get on top of it a kinetic term of the scalar field and a self-interaction term with 4 derivatives. All the other terms that you can write down with 2 or 4 derivatives are inessential, once again. And here in the bottom part, you can once again see the phase diagram that you get out of it. Here you have, again, 2 essential couplings, Newton's coupling G and this G d phi 4, which is the scalar self-coupling. And now you see 4 fixed points, A, B, C, D. A and B are really the fully interacting ones. C is a pure matter interacting fixed point, and D is the Gaussian fixed point. But now there is some more recent work from this year, actually, where we saw that probably these fixed points A and C are truncation artifacts, but B and D are very likely stable. So it's really more like the situation as in pure gravity, that you have a single fixed point, this fixed point B in this case, which has one relevant, one irrelevant direction. So it's completely predictive, no free parameters. Some work in progress with Alessia is basically doing the same thing, but instead of adding a shift symmetric scalar, adding the photon. And this gives you a couple of more essential couplings. So in total, we have 4 essential couplings here. Here you also see this non-trivial gravity matter coupling, y times f squared. And what we see here, well, it's work in progress, so it's not completely converged yet, maybe, but it's a very similar phase diagram to the shift symmetric scalar. So we have 4 fixed points where maybe 2 of them are not real in the end. But we are also investigating potentially the relation to positivity bounds in this theory and also to gravity bounds. But there are many more systems under investigation with other colleagues. So I'm thinking about fermions, I'm thinking about pushing these systems to higher order in the derivative expansion. So definitely stay tuned. And then last, -1 minute, let me just summarize. I think that falsifiability is at the heart of science, and it should also be at the heart of quantum gravity research. We really have to make this connection to observables. And at least from my perspective, scattering amplitudes are one very promising tool to probe quantum gravity. We always have to keep in mind that field redefinitions are allowed, but it also makes very clear the point that the difficulty really starts at the 4-point function. And we really need very strong results. And for this, we need a really high level of sophistication. So it will not be easy. And maybe as a remark to challenge you, or for you to challenge me, is that I think that this universality class of GR is very promising from the perspective of asymptotic safety, it points to a scenario where we maybe have 0 free parameters, and then maybe asymptotic safety is really string theorist dreams come true. With that, I want to thank you for your attention.
Okay, thank you very much, Benjamin, for your talk. Now we open the floor for questions. Yes, Anna Takareva.
Hello, everyone. Thank you very much for the very nice talk. I have a question, how, for example, the running of coupling in front of while cube term can be transformed into scattering amplitude? Just a technical question.
Basically, so if you look at this left diagram, so what I have in mind here, if I draw these diagrams, is of course a flat space scattering amplitude, where I expand the metric about, let's say, Minkowski. And then you basically just have to expand the y cube term to third order in perturbations around Minkowski, and then you read off the vertex, the 3-point vertex. And of course, it will also have some contribution to the right diagram, since curvature tensors are infinite order in metric perturbations. But it's really not different from computing the propagator or the correlation functions from the ancient Hilbert term. It's just a different operator, and then you expand around Minkowski space.
Well, there is no problem with that. I mean, how to take into account the running of this coupling, because in the effective action, it can be written like a effectively non-local operator, like run independent on the box. But then there is a question on which of the 3 wild tensors does this operator act?
That's basically the point that I was trying to make here. So if you have a 3-point function, you can parameterize the momentum dependence in terms of boxes acting on either the first, second, or third argument. But then you have this identity that box acting on while can be written in terms of the Ricci tensor or Ricci scalar, which are inessential. So really, if you take this seriously, the y cube term is local. At least the essential part of it is local. All the higher derivative, or like a box while times y squared, is inessential and can be removed by a field redefinition.
Yeah, but then how this RG running affects the amplitude? Or is it true that it's enough just to compute 3-level amplitude for coming out of a C cube term?
No, so the point is that the C cube term is completely local, and all the non-trivial momentum dependence is in the 4-point function. So at the level of these 2 diagrams, you can do field redefinition so that the left diagram is basically completely local, and all the non-trivial stuff comes from the right diagram.
Okay, I see. I think I got your point. Thank you very much.
Okay. Well, if you have further questions, you can discuss in the discussion section. Also, Sravan had a question. Please, let us postpone.
Yeah, I lowered my hand, so it's fine.
Yes.
Yeah.
Okay, so thank you again, Benjamin.
Yeah, thank you.
And the next speaker is Luca Buoninfante.
Hey, Breno. Hello, everyone. Yes.
You can share your screen.
Yeah. Alex, can you make me co-host also on my iPad?
Well, this is with...
Sorry, you want to make what?
Can you make me co-host also on my iPad?
Lucas' iPad. Is it you?
Yes, thank you.
Okay.
Because I'm using the iPad.
Yes. Sure.
Okay, thank you.
Okay, so the title of Lucas' talk is Decoupling Limits in Renormalizable Quantum Gravity. Yes, we can see your screen.
Yes, okay. So unfortunately, I cannot make it bigger because it's from the iPad. I hope it's clear enough.
I think it's clear enough.
Okay.
And you have 40 minutes. And in the last 5 minutes, I'm going to raise my hand just to show that you have
you only
5 minutes. You can start.
Okay. Thank you very much. So thanks, Breno, and thank you very much, all the organizers. It's nice to have again this meeting this year, and it's nice also to give a talk this time and not being an organizer. So actually, the initial title of my talk meant to be the coupling limits in renormalizable quantum gravity, but then since it is still a work in progress, I would say maybe it's better to say some remarks on renormalizable quantum gravity. And indeed, I would say that I would like to, let's say, divide the talk into parts. A first part where I just give some motivation for renormalizable quantum gravity. Maybe most of the things I will say are more or less obvious to some people, but I would like to mention them anyway, because here we are at this workshop and it's nice maybe to discuss different point of views during the discussion sessions. And the second part instead will be more towards this work in progress. So the idea is basically just to structure the first 10 minutes on this motivational part of renormalizable quantum gravity and then going towards the work in progress. But just to set up notation and the problem, I don't need to, let's say, tell again what are the problem of GR. Actually, Alessia and Benjamin did already a good work. So let me just say that the following extensions of Einstein general relativity, as we also have heard yesterday, is strictly renormalizable. Okay, and this condition of strict renormalizability is true in d equal to 4 for this action. Now here, just for convention, I'm defining the Planck mass in this way. Okay, so basically I'm introducing an extra parameter here, but it's just a convention because this one in general would keep track of the expansion in a fluctuation of the metric H mu. So the usual story about this theory is that basically, for instance, usually we say, okay, let's assume that lambda is small, then we can imagine that we can expand around Minkowski background, where H mu will be some gravitational fluctuation. And then we compute the propagator, and here I'm just writing a schematic form for the propagator, just the gauge fix independent part of the propagator, and we see that basically there will be an Einstein component where there will be the plus minus 2, let's say, degrees of freedom of the massless graviton. Then there is a spin 0 extra mode that basically comes from this R square. And then there is a spin 2 massive mode that comes from this Weyl square. And let's say the problem that usually people talk about when dealing with this theory is that because of this minus sign appear in the propagator, this spin 2 massive degree of freedom is a ghost. And this is the reason why such a QFT of gravity sometimes claim to be pathological when quantized with the standard conventional methods. Okay, so this is just to set up, let's say, notations and convention for the several parameters in the Lagrangian. And also, let me say that I will work, of course, as you can see from the action, I will work with this signature, minus plus 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 plus. So the outline of the talk is the following. As I said at the beginning, there will be a first part that will be basically just, I would say, motivational. And I would like to present this first part just in 5 minutes and give my opinion and why I would insist on working on this type of theory. And then the second part will be more towards the work in progress. Okay. Here there is already some spoiler, but basically in the second part, what I will try to ask is the following question. I will just ask first from a pure mathematical point of view without caring about physics. Okay, just take the action and ask what are the limits when I take alpha going to infinity or beta going to infinity. So I want really to see what happens to the degrees of freedom to interaction coupling in these two limits, in both cases in which lambda is 0 or non-zero, where lambda is the cosmological constant. And what we will see, what we will notice, is that the presence of a cosmological constant can play a non-trivial role when taking these limits. And we will also especially be interested in this beta going to infinity limit, so basically the coefficient of I square going to infinity. And especially there, we will see that having or not a cosmological constant will give a completely different meaning to this limit. And since, as I said, it's a work in progress, basically, I think we will leave as a work in progress some of the things, or maybe a good part of the things. And we will also highlight some points for possible discussions, maybe during the discussion session. So let's start this 5 minutes part of the talk with this motivational part, okay? So we know at least 2 facts that, for instance, if you just take the Einstein-Lagrangian alone, okay, so basically we just take this Lagrangian linear in the Ricci scalar, we know that at least this Lagrangian is, if you want to use just gravity, for instance, to describe our universe, we know that this fails at least in 2 cases to, yes, there is a question, what I mean by strictly normalizable. Yes, thanks for the question. So what I mean with strict, for instance, if you take the interaction of the standard model particle physics, all the electroweak and QCD interaction, they are strictly normalizable. Also, this Lagrangian of gravity is strictly normalizable because basically you can notice that all physical couplings have non-negative mass dimension, and at least one is dimensionless, which will be the gauge coupling. Okay. So for instance, instead, you can have also supernormalizability when all the physical coupling will have positive mass dimension. Okay. So with the strict normalizability, I mean at least one will have will be dimensionless and the other will be non-negative. And this is exactly what happens, for instance, with the interaction in standard model. And for gravity, as I will also point it out later again, this is a unique, actually, and very nice possibility for a strictly normalizable theory of gravity. Okay. That goes beyond, of course, Einstein GR that is non-normalizable. So I hope the meaning of strictly is now clear. If not, okay, good. Thank you. So let's start with this motivational part. As I said, if we just take GR Lagrangian alone, where we GR Lagrangian just mean a Lagrangian is a linear in the Ricci scalar, this is not for sure enough if you want to describe the current accelerated expansion of a universe, and for instance, CMB anisotropes. I think we all agree with that. And if you want to do, for instance, just observation, we see that GR alone fails to describe these 2 physical scenarios. What we would do logically is just to say, okay, let's do some phenomenology, and let's write down some simplest model to describe observations. And we know actually very well that, for instance, if we add to the Einstein-Lagrangian, to the GR Lagrangian, a cosmological constant term, and some scalar field with some suitable potential, plus standard matter contribution plus dark matter, and so on, we can describe a nice evolution of our universe. Here, of course, I'm not worrying about the problem of cosmological constant and so on. I'm just saying that if you put it, this is a good explanation for the evolution of our universe. And of course, we can fix parameters inside this extra term by matching the observation. But from a theoretical point of view, of course, what we should ask, I would say, maybe we all agree on this, is that whether those additional terms that we have here, for instance, in the Lagrangian, that are very useful to describe observation, can be somehow generated or derived from some guiding principles. And what I mean with guiding principle, so a logical way to proceed is to see whether what has worked in the past, for instance, for the standard model, can also be useful somehow to describe some gravitational phenomena beyond Einstein GR. And what has worked in the past, what we have learned, for instance, is that in the past, the framework of quantum field theory and the criterion of strict normalizability was a very powerful tool to select fundamental theories. Indeed, this has worked fantastically, I would say, with standard model interactions. So what I would say another question to ask, once we see that there is something that goes beyond Einstein GR, for instance, right? And one thing you could ask, okay, maybe I can explain those extra term in the action that I shown here, just by imagining, okay, I introduce some new matter field, some new couple matter to gravity and so on. But I would say this is still some construction done by hand. My main point here is to say, okay, let's just take gravity and let's see whether with gravity, by requiring some conventional, let's say, guiding principle, we can also go beyond Einstein GR and describe more physics that Einstein GR cannot describe alone. So the idea here, of course, logically, I would say is a very logical way to proceed, is then, okay, we know that Einstein GR is not renormalizable. But then let's use the criterion of strict renormalizability to select maybe a theory that goes beyond GR, that extends GR. We know that this criterion has worked for all the interactions. Let's see whether this criterion can be useful also for describing some new gravitational phenomena. Of course, if it fails, then we should do something else. But if it doesn't fail, and we see that actually can be useful somehow also to describe nature, part of nature, then let's try to understand the theory better. That's the philosophy. That's the logic I have in mind. And of course, if you apply this, let's say, if you apply this paradigm of QFT and criterion of renormalizability, as I said in the second slide, there is this fantastic Lagrangian that comes out. And of course, here what we have extra parameters. We have parameters in the which are in principle, like, I mean, in a quantum field theory, larger parameter, you can renormalize them. And in the end, you will have some physical parameter that you can match, you can fix with observation. Okay. Now, for instance, we know if we just do that, we take this Lagrangian, you see that both lambda is naturally generated by normalization. So you must include it for the normalizability of the theory. And so you can just use it to fix. And so basically, naturally, you get from this theory also a cosmological constant. Now, I'm not saying here that I'm not talking here about problem of cosmological constant and so on. I'm just saying that you get a parameter from just requiring normalizability, and then you fix it with observation. Moreover, you also get a term, which is this R square. And we know very well that this R square term contains or introduces an additional degree of freedom, which is a scalar degree of freedom. Not only, it is a scalar degree of freedom with a very well suitable self-potential. And is very well suitable to describe, for instance, the inflationary scenario. Indeed, sometimes this GR plus this R squared term is also known as Starobinsky model. And it can give a fantastic explanation for inflation, and through which we can also understand how CMB anisotropy is. The CMB anisotropy that we observe from the quantum fluctuation of this scalar field. So I would say that, of course, here we have still an extra term that is the one that was creating problem, as I said before. Okay, but you see, my point here is that just by requiring the same requirement that we ask for other interaction, which is basically the criterion of strict renormalizability, we obtain something which is useful to describe nature. It's not just mathematics. It's something that is useful to describe nature. It just comes from requiring a principle, which is that of strict renormalizability. Let me call it guiding principle. It's not really a principle, but it's a criterion that has been used, and actually it seems to be partly successful also to describe new gravitational physics beyond Einstein GR. Indeed, if you accept these facts that I've just said, you may agree or disagree, of course, because you can start with other assumption, then take another approach. But if you accept these facts, okay, in my opinion, then very important implications follow. One is what I just said, that we have another successful confirmation of this criterion of strict renormalizability in the framework of perturbative QFT. Okay. Then, if you take CMB observation, okay, CMB observation, actually, if we take this theory, what they are telling us is that they are providing a test of higher curvature of gravity. And actually also an indirect, I would say, proof of quantized gravity, because somehow this scalar degree of freedom is in any way a gravitational degree of freedom in this theory. And you are quantizing it. And the third point, contrary to some beliefs, usually people say that Starobinsky is just Starobinsky inflation is just a model, but I would say no, because if you take this theory, Starobinsky inflation is not just a model, actually can be embedded in this renormalizable theory. It's not a model anymore. So I would say that this is my main point. Okay, these are the main reason why I find this theory very interesting, not just from a mathematical theoretical point of view, but also from a more physical point of view in terms of experiments and observation. So this is the reason why I insist I would like to understand this theory more. Of course, here there can be disagreements, but from my perspective, there would be the possibility, because of course, the natural question to ask now is, okay, fantastic. You told us very nice things about what does this part of the action, but we know that this piece here contains a ghost. So in principle, this ghost can be problematic. So there are two things to do. I guess some people could just say, okay, there is a ghost, then let's throw the whole theory with all the nice features that it has, and let's do something else. Or the other possibility would be, okay, there is a ghost. We know that part of the theory has been fantastic to describe physics also beyond Einstein GR. Then, given this, let's try maybe to understand this piece better. And indeed, I will basically opt the second option. So try to understand the role of ghost in a strictly normalizable quantum gravity better. Also, before moving to the main part of the talk, let me just stress some interesting features of this theory. It's just a quick review here. Is that, okay, the loop expansion here is not controlled by alpha and beta in front of R square and by square, but it's controlled by the inverse of these parameters. And also, as Benjamin said in the previous talk, okay, if we take this theory as a renormalizable theory, alpha and beta, they are not in essential couplings because they contribute to new degrees of freedom. So this is a main difference if we compare this theory, for instance, with the standard EFT approach to Einstein GR, where the higher curvature term like R square and pi square in vacuum can be just thrown away by a filter definition because they become inessential if you work, for instance, the universality class that Benjamin was mentioning. And also, very interestingly, if, for instance, we look at the beta function for this parameter alpha beta, and we work with this alpha and beta positive, which are needed in order to avoid tachyons, at least I will show later. If we make this assumption, then it follows that G2, so basically this parameter here, is asymptotically free, whereas G0 can grow logarithmic with the energy. So it's not asymptotically free. It can be asymptotically free, for instance, if we opt for negative sign for this parameter. Okay. And actually, this computation has been done by several people with several developments. And I would like also to mention that more recently it was also displayed by Marco Piva, where he showed that basically, if you introduce higher spin matter coupled to this theory of gravity, you can actually, I don't remember now which type of higher spin, but with some choice of higher matter field coupled to matter, you can also achieve asymptotically free for this coupling here, if I'm not incorrect. But this is not what we're going to do. We're just going to take a Lagrangian, which is one I showed before, and we are not going to work about matter in this talk, at least not in the main part of the talk. Also, a nice feature also of this theory that distinguishes, I would say, this strictly normalizable theory from all the strictly renormalizable theories that we have in the standard model is the following fact. For instance, if you take electroweak theory, you take WW boson interaction, you know the WW boson without Higgs is not renormalizable, and also the three-level amplitude grows with the energy. But if you introduce the Higgs, you can achieve renormalizability. You can also improve the behavior of the three-level WW amplitude. But actually, this thing that does not happen here in the context of renormalizable quantum gravity, because if you take the three-level amplitude, graviton-graviton scattering, what happens is that basically the three-level is the same as Einstein GR. Okay, so you still have some growth with the energy to the square. In my opinion, this could be some sign of the presence of semi-classical black hole states in the spectrum as non-perturbative degree of freedom. It must be taken into account at some point towards Planck scales. But anyway, there are different, I would say, opinion on this. Here, indeed, for instance, Holdom recently has also proposed a different perspective about this. Last thing about this initial part, which has been a bit too long, I would say, is that recently, of course, there have been many proposals to recover unitarity with ghosts in normalizable quantum gravity. For instance, there have been approaches with negative norms for the ghost, where you can basically get minus sign here and minus sign here, and so still satisfy the optical theorem. You can work with a ghost that is an unstable particle, so somehow you can restore unitarity for time larger than the lifetime of the ghost, or you can even replace the Feynman I epsilon with a new prescription, which is called Feynman prescription, through which you can convert basically this ghost into a purely virtual particle that never appear on shell. What we are going to do in this talk now has nothing to do with any of these approaches, and I will try to keep as more general as possible, in the sense that what I'm going to say, I hope, will not depend on any of this approach. Okay, so any of this approach should not affect what I'm going to say. Should be independent. And so let's move now to the second part of the talk. Okay. I hope that this first part, where I just try to give some motivational reason from my side, was clear, but of course can be debatable and we can discuss later. But then I would like to move to the second part of the talk. And the main question, I would say, in the end will be, what happens when I take this limit to the theory? I will just have this question classical, like I just take a Lagrangian as a mathematical limit. I will not worry about physics, about loops and so on. I will just say, let's take this limit and see what happens. Then afterwards, we will try to understand some physical implication of this. Okay, so that's the point. And let's do it. But to do that is convenient to rewrite the action into a more convenient form. So basically, you see here, we know that there are extra degrees of freedom, but they are somehow hidden in this curvature square combination and so on. Because you can say, okay, the spin 0 is all here, the spin 2 is all here, the additional one. You know, it's not true. They are mixed also with the Einstein part. There is a mixing among these terms. So the idea is to first rewrite this action in a more convenient form, where we isolate the spin 2 massless, spin 2 massive, and spin 0 massive. Okay. Let's start with the spin 0 field. Okay. And this can be done in the following way. We can introduce an auxiliary scalar field. I mean, this is well known in the literature. We can introduce a scalar field chi, okay, and rewrite the action in this way, where this SW is the Weil square part. Okay. Then with the conformal transformation, then we canonically normalize the field, because you want canonical normalized fields to really understand how they behave. And then what we end up with is the following Lagrangian, following the action. And this is the spin 0 part. But the important point I would like to stress here is that when we have a cosmological constant and we try to diagonalize the degrees of freedom, we automatically have to, we are forced to rescale the cosmological, we are forced to rescale the Planck mass. You see, here we will have a gamma bar. We do not have any more gamma over kappa square, which was the M Planck square before. But there will be some rescaled Planck mass when lambda is non-zero. Then the parameter M naught square will be the mass of this scalar field. And it will be basically the ratio of gamma over alpha, where this gamma is the one without bar. It's just the starting one. Okay. And the idea is basically, since we want to do some perturbative approach, we should just find a vacuum for this phi and expand and see how the interaction look like. This idea. If we do that, basically what we can see is that we will generate some time. I mean, we have to expand in phi, for instance, the vacuum, right vacuum to choose is phi equal to 0. We expand it, we will generate these extra terms, series, which will contribute to infinite number of interactions. And there will be two types of interactions. There will be derivative interactions of this type and non-derivative interaction. And the important thing to note is that interaction couplings depend on lambda. Now let's do the same for the spin to field. Okay, the spin to field, again, the computation has been done also in the past, but I would say that recently there was, I think for the first time, something done with the cosmodular constant by Anselm and Piva. So I'm going to follow more or less what they're doing, except some different additions. And what we have to do basically here is the same. We have to introduce some auxiliary field. Okay. After introducing the auxiliary field, we make some method transformation to basically unmix the graviton from GR, the massless spin 2, and the massive spin 2. Then we canonically normalize our field. And in the end, what we get is a new action, which is equivalent, where there will be basically an Einstein-Hilbert part with some rescaled Planck mass again, because there is a non-zero cosmodular constant. There will be the spin 0 part that we showed before, where this G mu nu will be shifted by this transformation. And then there will be the spin 2 part, massive, that will contain the F mu nu field, which is basically this Gauss field. Okay. And again, I would like to emphasize that the expression for this rescaled, let's say Planck mass here, is dependent on alpha beta, and this depends and comes through a non-zero lambda. And again, here is the same. You can expand around the vacuum, F mu nu equal to 0, and you will generate basically a standard kinetic term plus interactions and no minimal couplings. So if you do that, you will get the standard Percy-Pauli Lagrange, okay, with some cosmodular constant, because we are not in flat space-time, but we are now still not making an assumption on Minkowski. Then there will be some no minimal coupling. And then there will be, again, two types of interactions. There will be interaction that will be generated by the mass term, when we expand the mass term G plus F, okay? And we generate like terms of this type that do not contain any derivatives. But then there will be terms, okay? They will be generated by variation of S, E, H. And this, of course, will also contain derivative interaction. And the important thing to notice here is that the presence of a non-zero cosmodular constant affects the mass of the spin 2 field, unlike the case of the spin 0. In d equal to 4, okay, I'm working d equal to 4 is important to this. And you see indeed that basically the mass of the spin 2 field is not just given by the standard Minkowski expression to usually write, okay, but there is an extra part that depends on lambda. It is not zero just because lambda is not zero. And actually, what happens is when lambda is non-zero and we work with a positive cosmological constant, we assume no tachyons and no tachyons. What happens is that we also get a bound, a lower bound in this mass value. Basically, this mass, if there is a non-zero and positive cosmological constant, cannot be smaller than 2/3 lambda. And actually, this result, I would say, for the fact that the mass can depend on lambda is already known from many years, especially like when there was all those work on critical gravity and so on. They were, of course, really playing. This depends on lambda. We're really playing an important role there. So this is a well-known fact that if lambda is non-zero, the mass of the spin 2 in this theory gets affected. Unlike, so it gets a different form if you compare it with the Minkowski expression. And also here you can look at the interaction couplings, and you will see that basically the one that is generated for instance, a variation of the S in Einstein-Hilbert action, it will have this form, and when lambda is not zero, you get extra dependencies. And this will be the one generated by the mass term. And also here you will have extra dependencies. And the important thing again is that basically when lambda is not zero, we get an additional dependence on beta. Okay. And as I said, since lambda non-zero also affect rescaled Planck mass, okay, automatically we will also affect interaction coupling for the massless graviton when lambda is not zero. And again, we get some type of formula like this. Of course, usually we say lambda is small, so we can neglect this and we don't see that. But here I'm going to say that there are regimes in which this lambda can play a crucial role, as we will see. Let's do first as an example. This is not what we are going to need in the talk. This is alpha with infinity. I just understand why the non-zero lambda can play a role. Sorry, Breno, how much time I have?
You still have 10 minutes.
Ah, perfect. Okay. You see, when let's do now, we have seen now how to rewrite the action in terms of splitting all the degrees of freedom. We have looked at the interaction coupling. Now the question is, let's see, just take now the spin 0 mode as an example, a starting example for the time being, and then we go to the spin 2. Let's take the spin 0 mode as an example. We will not need this limit because we're not important in the end, okay, but just to understand what happens with a simple case. Let's start taking this limit, as I said before, just classically mathematically, without caring now about the other physical issues and so on. We will speak about physics towards the end. Let's just try to understand what happens when we take alpha going to infinity and lambda equal to 0. This is the spin 0 Lagrange in some background, for instance, G mu nu bar. Okay. And the derivative couplings, you see, there will be the derivative coupling that does not depend, when lambda is 0, does not depend on lambda. So basically, it's not does not depend on lambda, so does not depend on alpha, because the dependence on alpha only comes from the fact that lambda is non-zero in the coupling, okay, or the derivative 1. So basically, this one will be finite in the limit alpha going to infinity. Instead, the non-derivative coupling, the one that is proportional to the mass, since the mass square of the spin 0 is proportional to 1 over alpha, of course, this will go to 0. Okay. And so, if you just ask what is the limit, this mathematical question, what is the limit alpha going to infinity for lambda equal to 0 of this Lagrange, what you get is this form. So basically, you just get an interacting self-interacting spin 0 massless. Okay.
Lucas,
yeah.
Sorry for interruption. Isn't it easier to do a field redefinition and push this term into that potential?
Which potential?
I mean, you have this in front of the kinetic term, so you have
this one.
no.
This one.
Okay.
Yeah. Of course, you can also move
that one.
Here,
if you do the field redefinition, then you move it to
same.
the potential, and it's easier. Why are you not doing it?
Because in that case, you will obscure the dependence on alpha. This is easier to understand where the dependence on alpha comes. Okay. If you do the transformation, understand what you mean, that you move here and you will have 1 minus exponential of something.
Yeah.
Okay.
Yeah.
Then there will be some depends on alpha, which will be, you will not see it. Okay. And there is not, you will not understand how to take the limit alpha to infinity. Then you have to see how the new field to define depends on alpha and so on. Okay.
But aren't you doing some truncation here?
No, here basically you say you have a Lagrangian here, and now you want to expand the rational background, phi equal to 0, for instance. Okay. And then you will have, you will have your high order interaction vertices and so on.
Okay.
You see here, this one. Here, by the way, I missed, there's a phi. 1 minus 2. Anyway. So this was the case lambda equal to 0. But now let's ask what happens. Where did they go? Now let's ask what happens in the case lambda non-zero. You see, when lambda is non-zero, as I said before, not only the non-derivative coupling, but also the derivative coupling now will have a dependence on alpha. Actually, 1 over alpha. And when we take the limit alpha going to infinity, what happens here is that basically also the derivative coupling will go to 0. So a non-zero lambda in this limit can play a role. And indeed, if you just ask this mathematical question, what you get to take this limit is just basically a free scalar field in some background G bar. Of course, I'm not considering the field, I'm just as an example to understand what's the logic, just consider this spin 0. Okay, but now, so this is basically just the recap of what I've just said. Okay, what is the situation?
Can I ask you something? Sorry.
Yes.
Can you go back to the previous slide? What do you mean by derivative couplings then? Because here you have a free massless scalar in the end, right? But you still have some interaction due to the metric coupling, no?
Metric coupling, you mean G mu?
The coupling between the metric and the scalar field is still there.
Sure. No, what I'm saying is,
only
as an
derivative.
example, no, I said as an example, let's take, for now to understand what I want to do, let's just take some, let's take spin 0 in some fixed G bar, in some background G bar. Okay. I'm going to ask also what happened to interaction with the H mu, for instance, yes.
Okay, but maybe I just missed before when you were distinguish derivative coupling and non-derivative.
Yes, what I mean is the following, sorry. So you see, if you expand
because now
this,
you say that they are both to zero, they went both to 0.
Yeah.
But you still
because
have
you see,
derivative coupling.
here, this goes like 1 over gamma bar, and gamma bar there is alpha.
Yeah.
So basically 1 will go to 0, even if there is lambda equal to 0, because there is a dependence here. So the mass term will go to 0 anyway. And the derivative 1 will survive. But if lambda is not 0, when we take alpha going to infinity, also this term.
You mean derivative interaction with self?
Yeah, no, I mean the one that are basically proportional to this one. You see,
but which contains also phi again, right? More than 2 phi.
Sure.
Okay.
Well, you see, in the end, we'll only survive this. That's what I mean. So I'm distinguishing like derivative part and non-derivative part, which multiply all these interaction terms. Okay.
Yeah. Okay.
That's what I meant. Sorry.
Thank you.
Okay, Breno, please. There were already questions. Maybe I can take 1-2 minutes more.
Yes, sure. Let's make it 45 minutes in total.
Okay, thank you. So this was just the case of the scalar field in some background to give to understand what was going on. Okay, but of course, interesting question to ask is the following. Please give me this 5 minutes, and then I will close. Okay, because I think it's very interesting. Now we want to take the same for the spin 2, and then we want also to discuss, for example, what happens to interaction with other among all the degrees of freedom. Okay, the first thing to do is first try to understand what happened to the spin 2. Okay, massive spin 2 in some background G mu bar. Okay, and then we will see also all the interaction with the metric and so on. But again, we also here have to distinguish between lambda going to lambda 0 and lambda non-zero. When lambda is 0, and we take this limit, again, there will be a similar story like for the scalar field. There will be those interaction terms that comes from the variation of the Einstein-Hilbert that do not depend on lambda. And there will be the terms proportional to mass term that will go to 0. But here now we have to be careful, unlike the case of the spin 0, because here now what happens is that also here when beta goes to infinity, we have a massless limit. That's true. But since we have a spin 2 field, we know that, for instance, people working in massive gravity, we know that taking a massless limit must be done with care, because sometimes can bring to discontinuities of degrees of freedom. Okay, let's just make a brief digression of what happens usually in massive gravity. For instance, let's take this Lagrangian, and let's take a m going to 0, m2 going to 0 limit, massless limit. What you would do, just kill this, right? But then, naively, you would say, okay, I have just a Lagrangian, which is the one of GR, linearity GR with some interaction, and then I should expect just gauge symmetries, and so 2 degrees of freedom. So how come you go from 5 to 2? So there's a discontinuity. So basically something has been done in the wrong way. Something was not accounted in the proper way. Indeed, if you do things correctly, by using, for instance, the Stuckelberg trick, you can restore basically all these extra degrees of freedom. Indeed, what you have to do basically you have to split your field F mu nu in basically a plus minus 2, plus minus 1, and then a scalar degree of freedom that will have their own gauge symmetries. Okay, and then after you do that, you can take the limit m going to infinity. Okay, because you see there will be some extra m dependence in these two parts that are needed for the canonical normalization of the fields. Indeed, when you do things correctly, in the end, you will still have your 5 degrees of freedom. So you will have a first Pauli for m going to 0, which will be the plus minus 2. And then you will have plus minus 1 and a plus 0, spin 0 degree of freedom. And then, of course, we will have interaction in general. And usually interaction in massive gravity are a problem because you can encounter some strong coupling when you take this massless limit. Why? Because, for instance, if you just look at this form and you have some cubic term, you will have some term that goes to like 1 over m2. So basically, when you take m2 going to infinity, when you take m2 going to 0, massless limit, which would be the beta going to infinity in the normalizing Boccano gravity, this limit here, massless limit, could be divergent, could create some strong coupling. So the question is, does this happen or not in the context of renormalizable quantum gravity? And since there is not much time here, the point, which is very nice to make, was first asked this question actually by these two people. But here I would like to sketch a different, more general different proof, is that basically this strong coupling does not arise if you work in d equal to 4. Why? I would say because d equal to 4 is the dimension for which you have also the renormalizability, because if you take, for instance, d equal to 5 and so on, for this quadratic gravity, you don't have a renormalizability. Indeed, what happened is the following. You see, if you do a Zuckerberg decomposition of your Lagrangian, you get the following. So you get extra terms, okay? And if you take this term here, you can see that in principle, this term could give rise to some 1 over m2 that can diverge when you take the massless limit. So you should make sure that this does not happen, that there is some proper cancellation happening in d equal to 4. And this is what happens. And this can be shown in the following way, okay? I just need 2-3 minutes, but I haven't finished. What happens is the following, basically, is that you can show that by making a filter definition, okay, you can kill all the possible terms that would have given you discontinuity, or would have given you this type of divergent behavior in the massless limit. Why? Because you see, you have these 4 terms, which is very nice, I think. You have these 4 terms, and all of them could, in principle, generate some 1 over m divergence in the massless limit. But you see, when this term would disappear, only when we can choose A and B from this filter definition, such that all the 4 conditions go to 0. Okay, all these terms go to 0. And the condition are this one. If you look at them, they can be all simultaneously satisfied only when d equal to 4. So this means that when you take this massless limit, unlike standard theories of massive gravity, you don't have a problem of strong coupling below Planck mass, for instance. Okay, you don't have this. Now, last 2 slides, I'll say. Of course, this is basically what happens. So you don't have this problem, but you can still see, for example, what happens with your interactions. Okay, you don't have strong coupling, but interactions still survive here. Indeed, what you can do, you can rewrite your Lagrangian and so on, and then you will see that there will be still interaction between h mu, between all the modes that you have in your graviton and so on. So basically, beta going to infinity for lambda going to, in the case of lambda equal to 0, beta going to infinity does not kill all the interactions. You can see here, because there will be self-interaction surviving, a mutual interaction between massless and ghost graviton surviving, and so on. So there will be many interactions surviving. It's easy to see that there is no point to do that. But the main point I want to stress is that basically this limit beta going to infinity, which is the massless limit for lambda equal to 0, does not give rise to divergent couplings, unlike standard, for instance, massive gravity theories. And of course, now the next question would be, what happens when lambda is non-zero? Because you see now here, when lambda is non-zero, you don't have any more a massless limit. So the meaning of beta going to infinity changes drastically. Because when you take lambda non-zero, you take the beta going to infinity limit, what you get basically is that, okay, apparently this interaction term here, the one coming from the variation of the Einstein-Hilbert, the mass term go to 0. But also here you should be careful, because you are getting here a mass term which is equal to 2 over 3 lambda, and this value of the mass is the value of the mass of the so-known partially massless theory of gravity. Let's have also here a very quick, brief digression, and then conclude. Okay. What is partially massive gravity in standard theories of massive gravity? Basically, if you take this Lagrangian, okay, you say, okay, let me naively take this limit, okay, and then work with the Lagrangian. Actually, you cannot do that. You must be careful, because if you take this limit, you get, for instance, this quadratic part for the Lagrangian, forgetting about interaction. This Lagrangian has an extra scalar gauge symmetry, which is given by this one, which would kill 1 degree of freedom, so would go from 5 to 4 degree of freedom. So also here, as it happens for the massless case, where you may lose some degree of freedom if you're not careful, you should be careful and try to do things consistently. So also here, what you should do, you should introduce some Stuckelberg field in this way, okay, where this lambda, this operator nabla takes into account of this difference here. And when the difference goes to 0, you are, in principle, you are taking this, let's say, partially massless limit. Okay. So once you do the Stugelberg field, and you do things correctly, you can restore again the same number of degrees of freedom, because what you will have is that you will have in the end, the 5 degree of freedom of the massive graviton will have one partially massless graviton, which has 4 degrees of freedom, plus 1 extra degree of freedom. Okay, which has actually a very peculiar feature that we will discuss later at the end, the discussion. Okay, so you see, when you take the beta going infinity limit, for instance, in the case of normalized quantum gravity, you need to be careful anyway, because you may lose pieces, so you need to do things in a careful way. Indeed, okay, let me just say here, basically, what can happen in principle? You see, the same as in the massless case. Here also, because of this difference here that goes to 0 when you take the limit, okay, what can happen is that once you introduce your Stugelberg field to restore all the degrees of freedom, there can be terms, interaction terms of this type that go like 1 over this operator, is called nabla, okay, which in our case would be basically 1 over beta. This one would be proportional to 1 over 2. In our case, this would be this one. So basically, interaction time will be proportional to beta. And so things could be divergent. In the same way, I think things could have been divergent in the massless case when you take massless limit. Okay. So also for lambda non-zero, we should be worried. We should really be careful to what to do. And now in this case, of course, we should ask the same question. What happens in the case of strictly normalizable theory? When you take lambda non-zero and take the limit beta going to infinity, would you avoid this divergent coupling, this type of strong coupling that usually you have in a massive gravity? Okay. Now, this is a work in progress. Unfortunately, didn't finish. Didn't really. I don't have a really complete understanding there. But the claims would be that since the theory is renormalizable, you should not get. You should get a smooth beta to infinity limit also when lambda is non-zero. Okay. And actually, since lambda is non-zero, and you have then a smooth limit, this beta going to infinity might kill a lot more interaction. For instance, the self-interaction of the massless graviton and of the plus minus duality of the ghost, those one will be completely killed. And may happen that also the interaction will be killed, because we will have basically explicit 1 over beta dependencies, extra dependencies when lambda is not 0, that apparently in the limit would kill all the interaction and somehow give some type of ghost decoupling. So, but this is, I would say, a claim is still a work in progress. So let's take it as a claim and let's stay tuned about this. And the last slide, okay. So as I said, I was a bit fast in the end, but I hope the logic was clear. And the point is the following, is that, you see, what I've done was just mathematical limits, just saying, let's take some lambda, some beta going to infinity, for instance, when lambda is 0 is not 0. But actually, we know that if we take, for instance, the energy behavior, the beta function of decoupling and so on in this theory, beta going to infinity may correspond to some energy limit. Now, of course, what I've done cannot be immediately understood as a energy limit. Things should be done more carefully. But of course, another question to ask is whether we can understand the energy behavior of the ghost in this limit beta going to infinity. So basically, whether the discussion I just made can be used to understand the high energy limit of the ghost. Because if yes, then the cosmological constant, actually, no matter how small it is, okay, but if it's non-zero, might really play some role in the really high energy limit beta going to infinity limit of the theory. Just because the way we collect the degrees of freedom of the massive spin 2, okay, is different from lambda going to 0 case and lambda non-zero case. Okay, just because in one case you would have the plus minus 2, plus minus 1, and 0 elasticity. In the other case, you would have a partially massless graviton, which has 4 degrees of freedom, and then plus an extra scalar degree of freedom. Okay, and this is the composition of the partially massless. Okay, it's something that you should expect anyway from, for instance, the Sitter representation and so on. So this is something that at least when you take this limit appears, and it would be nice to understand whether also at the energy, whether the energy limit should also be understood in this way. Okay, And the last comment is that actually most of the approaches that have been proposed, for instance, to deal with the ghost problem in this normalizable quantum gravity has been formulated in a Minkowski background, strictly speaking. And several extrapolations have been made, for instance, in curved space. And I would say some are also quite well justified. For instance, I think in cosmology, one can justify things, for instance, with the Fagan's prescription, there is some well justified method. But I would say more generally, I mean, we don't know whether we can really trust these approaches far from Minkowski. And also, usually lambda is treated as a small parameter. Okay, but what I just said is that lambda can play a role in some parameter space of this, for instance, coupling beta. So could this non-zero lambda really play some role and make us rethink again about some aspects maybe we have given usually for granted? And I don't know, maybe lambda can play a role in this theory of gravity just because it appears in the mass of the spin 2, and so it affects couplings and so on. Okay, so I'm sorry if I took some more minutes, but I will now conclude. And yeah, thank you very much for your attention.
Okay, thank you, Luca, for your presentation.
So actually, since there was discussion later, I'm not stealing anyone's time. Hope, I don't know. I hope.
Yes. And yes, the discussion started during the talk, so it's okay. So, so now let's open directly the discussion section, because there are already questions during the talk. So now we can have questions to all the speakers. I would like to ask the people who make the questions to turn on the camera.
Can I unshare? Can I stop the sharing?
Yes. Well, let's start with Juan Wu, who raised the hand first. Yeah. And I think it's also related to Luca's talk.
Yeah. First, thanks to the nice talk. I have a question. What happens if we use this theory for the ADS spacetime? If
no, I understand the question. So
if we use this thing, this renormalizable quantum gravity in ADS spacetime, we can imply the correspondent as ADS-CFT. If yes, the cost in the box can correspond with what in the boundary.
So yeah, thanks for your question, Wang Gu. So I'm not an expert of ADS-CFT. What I can tell for sure is that the sign of lambda will not affect the renormalizability of the theory. That's for sure. I mean, the sign will not affect it. But for sure, if you take a negative lambda first, I mean, I took from the starting a positive lambda because I want to, for instance, describe a late. I would like to have anyway, including this theory, the possibility to describe a late time expansion, accelerated expansion of the universe with a positive lambda. And also the discussion that I made about this partially massless gravity, it is only true for positive lambda. So for negative lambda, if you are in the zeta background, this will not apply. So some of the decoupling limits happen there. I don't know. I'm not familiar with those. But for sure, a negative lambda would change more than half of what I said there.
Okay.
And I don't know if what I don't know the question about if you have a ghost in the bulk in ADS, what would it be on the CFT? I mean, I'm not familiar with this dictionary, so I really cannot answer. I don't know if someone else has an answer about this. But...
Okay. Yeah.
Okay, now Ravan, I remember that Ravan had a question or Benjamin. I don't know if you asked
maybe I can.
but go ahead.
Yeah, well, my question is to Luca, but also it involves other speakers, especially maybe Benjamin. So, well, but maybe I'll just ask Luca first question related to this lambda. So, I mean, in Stella paper, there is a small presence of lambda, so he neglects it when he considers propagators or loops, right? So, but well, strictly speaking, when you have lambda, Minkowski is not a solution, so you will have to deal with de Sitter.
No, sure, but I mean, I think I agree with you that if you have not, I mean, in principle, to me, if lambda is non-zero, Minkowski is not a solution.
Yeah.
But at least in the Stella paper, the idea there was that he didn't put any lambda from the beginning. So it's like saying that the lambda will only appear as a counter term to cancel the divergences, but the physical value of lambda in the end will be set to zero. That was the point there, to not put lambda.
Yeah, if you set to zero,
lambda,
yes.
Yeah, if you put a lambda that is non-zero, you want to treat it as a small parameter. I think in principle you can still perform a perturbation theory Minkowski. That's what is usually done. But then you need to take, you need to also care. You need to also make sure that if you do this, you will have Tadball contributions that will appear, because since the background equation is not satisfied,
yeah,
there will be some term like square root of minus g h, which linear in h, which will contribute this Tadball. So we need to take that into account. And I think this. I mean, people know how to take these things into account. So
yeah, sure. But that it is important that lambda has to be kept small enough, and you do not deal with the energy, any modes of energy comparable to the lambda. So this is a very non-trivial thing, because I think.
I think that, so the point, the last part that I want to I was mentioning here is that basically, if you take, I mean, as a mathematical limit and just examine this parameter space, okay, of this theory, if you take beta going to infinity when lambda is non-zero, what happens is that the mass of the spin 2 becomes of the same order of lambda.
Yeah.
Okay. Or at least part of the degrees of freedom of the spin 2 becomes of the same order of lambda. So that's a case in which actually lambda is not negligible as compared to other parameters. Okay, which would be
This is a good point. Then you really have to deal in this limit. You really have to deal with the cosmological constant or de Sitter.
That's why the point was
where there are a lot of issues. Quantum, we know only renormalizability in Minkowski spacetime, and in this limit, de Sitter seems to be an important thing, and we do not know whether the theory will become completely renormalizable in de Sitter spacetime. It is not known.
No, I think the renormalizability is independent of the space, the background, right?
No. I mean, when you prove renormalizability, you have to compute the propagators, right? So it has the propagators are computed.
No, but I think there are techniques, covariant techniques to prove renormalizability of the theory. I mean, this is
covariant technique. I do not know. At least
I'm not also. I'm not saying I'm expert at that, but there are
space-time concept of propagator, and there are a lot of issues related to at least even quantization point of view. But okay, well, this covariant.
No, but I think renormalizability is not affected by the fact that you can change background. I mean, there are.
I don't know. Maybe if someone can comment about this, or is it?
I think I agree with Luca. I mean, you basically have to look at the heat kernel again in the end, right?
Okay.
And for that, it doesn't really make a difference whether you expand about zero curvature or finite curvature. I mean, the heat kernel has certain properties, and I think you still can make the argument that counter terms should be local, and then you have, like, coming from the mass dimension of operators, you have suppression with the UV scale. It's just that you would not count in powers of R, but in powers of, let's say, R minus 4 lambda, so like an on-shell, counting on-shell powers of the equation.
Okay, I understand at least the essence of. Well, actually, the question again goes to Benjamin. So in relation with keeping lambda small, well, when you have matter loops, or lambda will get running, right? So so you cannot keep lambda to some fixed value. For Luca, you pointed out in the beginning of your talk. So lambda, you can keep it, for example, observed value of cosmological constant. Well, you cannot keep it like that, because anyway the lambda will have running.
I don't think it runs, right? Why do you think lambda runs?
I mean,
it doesn't run in a physical sense, right? So in the sense of a physical momentum dependence, it cannot run because it's just what should it act on? Like momentum dependence means something like the D'Alembert operator acting on something. But if you look at the term in the effective action, what I call cosmological constant is really the constant part of the action without derivatives, and this does not have a running. But this is how it is used in cosmology. Cosmology is a little bit different. There, people talk a little bit more about effective, or what I would call effective cosmological constant. So something that has the same effect as a cosmological constant, and this could depend on space-time. So there's some subtlety here, because different people call this different things by the same name. But of course, you're completely right. I mean, there are loops, and you have to take that into account. But in the end, if you compute the effective action, lambda will just have some value.
Okay.
Yeah, there is also a comment by Antonio about, I mean, there are techniques, covariant techniques.
Okay. So, well, if I understand your conclusion is, okay, you can fix the lambda, whatever the favorite value, at all scales, physical scales. That means, let's say, from the Big Bang to present.
Yeah, I think if you take the lambdas, the parameter de Lagrangian, I think, yeah, I mean, it wouldn't be affected by.
Yeah, exactly. I mean, I just take, I don't know. So you give me Lagrangian, I do the computations, right? So if you give me lambda is small enough, okay, then there is no problem for example, Stravinsky inflation to happen. If lambda is huge, well, then there are issues, especially if the lambda is very, very large comparable to the scale of inflation. Mm-hmm. But if you say that, okay, lambda, you can keep it small at all, well, it's a parameter, it's a free parameter, you fix it to your favorite value, then okay. Then I do not really understand about this RG flows. It's not related to physics, or I mean, if in a physical scale, if you say that, okay, fine, then how do I test it? How do I test RG flow?
It's for you, Benjamin. It's not for me.
No, the non-trivial momentum dependence of the RG flow is just in the higher order correlation functions, right? So if you really want to compare to experiments, let's say LHC, you look at scattering events, right? You compute scattering rates and stuff like that, and how this depends on energy. But there you are actually looking at an observable which has some momentum dependence, like physical momentum dependence. And the relation between what you write down in the action in general and the scattering amplitude is non-trivial, of course. And this is where this minimal essential scheme comes in. This scheme just keeps those operators in your action that actually appear in the scattering amplitude. So there's a more direct relation from the actual physical RG flow to measurements.
What is the relation?
Well, yeah, it depends on your observable. I mean, let's say you you have some decay rate, let's say, at a certain energy, or you look at the energy dependence of a certain decay, and you compute the amplitudes for that, and then you find a relation.
Okay. Actually, this comes to another question. Well, of course, at least in your talk, the Lagrangians, you have shown the effective action with while cube and all. Well, if you compute scattering amplitudes, it's maybe impossible to test that in any foreseeable future collider experiments. But surely, such terms are really considered in cosmology, especially inflationary correlations. Then I'm puzzled how to translate your results in the context of scattering amplitudes, which are computed in Minkowski, to correlators. How do I use your asymptotic safety program to really test something in the same Lagrangian is considered and studied? So how do I make a relation between them?
So to be perfectly honest, looking into gravity scattering is really a different beast, because, as you say, I mean, you really have to look at asymptotic states in curved spacetime, whatever that means, right? That's a horrible beast to even make sense out of. So it's not really something that I'm looking at with a priority right now, because it's just there's certain conceptual issues with that that I don't know how to solve yet. What you can look at is, of course, flat space-time scattering of gravitons, but even that is a bit, well, fishy for these reasons. So a connection to of just pure gravity to cosmology is definitely hard. What I think is more promising at the moment, at least, to test what is going on in asymptotic safety, is to couple standard model matter and to see whether the amplitudes that you get with asymptotic safety are compatible with standard model parameters and compatible with unitarity, causality, like all these conditions, right? At the level of, let's say, photon-photon scattering or Higgs to Higgs scattering, all these scattering amplitudes that you can look at the impact of gravity. Is it the causal, unitary? Is it consistent with observations? This is like my midterm goal, if you want.
Okay.
There is a question by Anna Takareva. A comment.
Hi. That's just a comment regarding the program of asymptotic safety, compatibility with causality and unitarity on all these positivity bounds things. I would stress here that it's very essential to have an assumption of polynomial boundedness of the amplitudes, which may well not be there in asymptotic safety theories. So if there is no polynomial boundedness, then all positivity bounds based on dispersive relations just do not exist in the form normally presented in the literature. So the first thing to consider here would be to understand better whether asymptotic safety is compatible with polynomial boundedness of the amplitudes.
Yeah, of course. So basically, I completely agree with what you say. The bottom line is you have to compute a 4-point function to get this 2-to-2 scattering. And then you can ask what is the high energy limit of such an amplitude and see whether it fulfills standard bounds. This is the kind of goal that you have to aim for.
And moreover, it's not only high energy limit, it's high energy limit also on the all complex plane.
Yeah, of course. Certainly. Yeah. But it's just not an easy task. That's basically what I'm saying.
I appreciate that.
And we have looked at a little bit of model building in the past, like 2 or 3 years ago. And let's say we could show that there is at least a proof of principle that you can combine some versions of or some bounds with asymptotic safety. So it's not completely hopeless. That's what I can say.
Yeah, I mean, all these constraints which are imposed by positivity bounds on effective field theories are very kind of stronger than one would expect just from, well, yes. They just constrain all these couplings to some compact areas, but one has to have in mind that these constraints are derived under the assumption that amplitudes are polynomially bounded on all complex plane of Mandelstam variables, which might be well not be true.
Yeah.
I have a question to Alessia.
Oh, yes.
If she's around, yeah.
Yes.
Hi, Alessia. So in your talk, you kind of showing that there are well. First of all, it's interesting you show that in some Lagrangians, some non-local Lagrangians will lead to divergences in the entropy. Well, I have a technical question. So in your computation, so you are basically computing corrections to the Schwarzschild metric with whatever the theory you consider at the linearized level. So you're basically doing perturbation around the Schwarzschild metric, right? Then you are computing the wall entropy for that. Am I correct? Is this what you're doing?
The thing is, we are taking the case of large black holes, such that we can use an asymptotic expansion for the action. For the metric coefficients, and then essentially you can just use Wald entropy formula, and you know that that type of asymptotic expansion can come from a principle of least action with certain coefficients, and then one just replaces that in the Wald entropy formula. So in the Wald entropy formula itself, there aren't approximations aside from the fact that you are considering quadratic operators at quadratic order only. So you are forgetting about R-cube operators, for instance, but this is okay asymptotically, especially if the spacetime is asymptotically flat. And then the approximation, if you want, comes when you replace the metric, because that is the metric coefficients, because that is only the leading order correction. So the result is there for two leading order, but if there are infinities already to leading order, there are also for the full metric of large black holes. Nothing can be said for, it cannot really be extended to the case of small black holes, but it is already a problem to have a diverging entropy for large black holes with the finite horizon radius.
So based on this, do you think we can throw away the Lagrangians which give diverging entropies?
You can.
We can definitely disregard the theories which give divergent entropies.
Yes, so I mean, they are all those with the 1 over box or 1 over box 2n operators, unless you fine-tune the coefficients of the infrared non-localities to exactly cancel the divergences, because these divergences can have a positive or negative sign, and for special values of the coefficients, you can cancel the infinities. However, then the coefficients, of course, have to come from quantum gravity. So it is non-trivial to get exactly the coefficients that cancel the divergences.
Well, even before going to quantum gravity, a lot of these IR non-local theories are useful for dark energy. So
yes,
it is expected that there will be several constraints in the with dark energy observations in future. So we will definitely know precisely what
exactly. So there are these all of these bunch of models, the models by Maggiore and those by Desert-Woodard, and if you want, you can use the consistency of black hole entropy in order to fix the coefficients, so to have additional constraints. So you can do that phenomenologically if you want to make things consistent, but then of course you want a fundamental expression. So this specific coefficient should come naturally from fundamental computations.
Okay. Okay.
Yes, Huang Hu.
Okay. I have question for Alexander Sabratina. The information paradox in the you have a correction in a black hole entropy. So this correction in information paradox, what happened?
Well, as I mentioned, the information loss is a problem whose resolution, in my opinion, depends on the full dynamics from the formation of a black hole till its complete evaporation, which includes highly non-perturbative effects, and in particular Planck scale physics, where one cannot really extrapolate from the classical dynamics, and in particular only using the entropy corrections that I used, because also in the last stage of the evaporations, all curvature operators matter, and therefore it isn't really possible to extrapolate from the case of large black holes, so asymptotic formulas where GR more or less works.
Okay.
So I cannot really, from what I have done, I cannot infer much about the information loss.
Yeah.
It's a nice question, Alessia. So, are there any limitations to apply Wald entropy formula?
What do you say? Issues?
Are there any limitations to apply Wald entropy formula?
Well, there are a number of assumptions that come into the derivation of a Wald entropy formula, and most of them, so all of them, are fulfilled by our computations. And as I mentioned, there is the caveat of the fact that the operators in the actions must be locally constructed. And for this reason, one needs to essentially rewrite the action in terms of additional fields and terms containing Lagrange multipliers. And with this intermediate step, one can apply Wald formula and then derive the entropy on shell.
Okay, okay.
So we still have 10 minutes, but if there is any other question, or maybe we can declare this session finished. Do you agree with that?
Yeah, I think if there are no more questions. We need some time to relax before next session anyway.
Yes, yes, yes. So we have more time between the sessions. So thank you all the speakers and the people who attended. And well, see you later. Oh, Antonio Pereira raising his hand. Oh no, it's the clap. Okay.
You.
Okay.
Bye-bye.
Alexei, hello, here is Irina. Could you please make me a co-host for a few minutes? I will try in this computer to share screen. Could you please
Yes,
now?
yes, no problem. Yes, you
Bye,
can share.
everyone.
Okay,
Bye.
thank you. Thank you. I try
Thanks.
to make.
Thanks all the speakers. And Brano.
The same problem. Yes, откройте системы. The same problem. Alexei, if there is some problem, so your suggestion is just to renew the Zoom system, because it's asked